Okay, welcome back. On the last video, we were solving this example about Cartesian coordinates, and as I already have commented with you, I'm using two versions of this book, Introduction to Robotics, which is a version with a Portuguese language, which is the second edition, and another version with the English language, which is the third edition. And as we already have saw, we got some conflict on the examples. Um, this example that we solved on the last video is the example 2.17, and we got the same example, but you will see uh, that is with different coordinates, but entitled as the example 2.18. And let's see this example, and we will use a different notation, different from this that I used on the last video, arctangent. We use this notation. You will see A10, and again the notations, they are very important. Okay, so let me write this the statement of this example, and again it's the same example with different coordinates and entitled different as well. So is this the example 2.18, and it says that, let's suppose we desire to place the origin of the hand frame of a cylindrical robot at, and these are the coordinates 4, 5, and 6, and asked to us to calculate the joint variables of the robot. So as we have already um, made the analysis on the cylindrical coordinate part 3, now we know that these three first columns is referring to the orientation, and we can see on this description as well. So let me find it. Right here. The three first columns represent the orientation of the reference frame, and the last column represents the origin. And also, I couldn't explain to you uh, exactly this last column. Um, place each element on the graphical, uh, but throughout, as we approach more of this content, we will find out, um, as is already saying, that is for position, and this gives us the sense, a good notion that uh, as as this draw. So those three first columns, if they are for orientation, and we know that it is on this point, on this region. So if I'm not wrong, the position is referring to the position of this point. Okay, so let's continue. And as we already have solved this example 2.17 from the second edition, we got now a good intuition on how to solve, and let's apply the same logic to solve this example 2.818 from the third edition. Okay, so I will just change right here the coordinates. So right now is 5, 4, and 6. And the solution, as we already have done on the last video, we had to define the components of the localization, of the region, of the reference frame, of the matrix for the given values. So that's easy now for us. So defining the components of the localization. So R cosine of alpha is equal 4, and R sine of alpha is equal 5. And for the length L, the value of 6. And also let's use the trigonometric relation. Tangent of alpha is equal sine of alpha divided by cosine of alpha. And apply now these components. So R sine of alpha divided by R cosine of alpha, and we can eliminate the R, and we are left with, so now is 5 divided by 4. And as I told to you, now we use a different notation. We wanted to know alpha. So in order to know alpha, we will take the arctangent. So alpha is equal arctangent and that is the notation of the book, but we can also use this notation, arctangent and 5 divided by Okay, that's it. So now let's calculate. Okay, let me open the octave. So we will do alpha, and we have to do type this comment tag equal a10 2d and our coordinates y and x, which is 5, 4, and 5. And this is to calculate in degrees. Okay, 38.6. So this is equal 38.6. And now doing the same as we have done on the first example, the example 2.17 of the second edition. We just have to take this relation and we might obtain the same value for R. So R is equal 4 divided by cosine of alpha. So is 4 divided by cosine of alpha is okay. And same right here, R divided by 5. R is equal 5 divided by sine of 38.6, which is equal 6.4. So the final answer is R is equal 6.4 units with a alpha of 38.6 and L equals 6, and this is the answer. Okay, let me write right here. This is from the third edition. Third edition. Now, from the second edition, from the second edition. So let me write the position and orientation restart it. Of a cylindrical robot or given. So that is the matrix, which represents the position and orientation of the cylindrical robot. One zero 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 0 1 0 0, and on the, if I'm not wrong, on the first part of cylindrical coordinate or second, we have done a analysis. So now you know that the column which represent the orientation of the end effector, and we confirm this, the elements, the columns with the elements that represent the position of the end effector is that one, and as this is z, y, and x, so when we saw this, it turns obvious. So we can, if we extract these elements and think in form of coordinates, so I will go to the image where we can understand better what I'm saying. So this image, this draw, right here. So these elements represent the orientation of the end effector right here. So as L is equal Z, which is equal 9, so okay. Nine. And this last line is the in the scale factor W. And asked to us to find the matrix which represent the position and orientation original position and orientation. Okay. of the robot before got restored. Before got restored. And the solution is once R is always positive, and this makes sorry um, and sine of alpha and cosine of alpha being positive and negative. Um, Sine of alpha and cosine of alpha being positive and negative respectively. Then alpha is on the second quadrant. Okay, we have just to apply the same concepts that we have applying on the first examples of this nature. So let's use this trigonometry relation. Tangent of alpha is equal sine of alpha divided by cosine of alpha. So this way we got now is very interesting. We can learn right here something based on what we already have saw. Right here, what is given to us is this matrix, is these coordinates, and using the transposed form. So if you don't watch the cylindrical coordinate part 3, in which we do this analysis, so and we assume that the order of these columns is this one, two, three, and that is the last column. So these three first columns is representing the rotation of the end effector, and as you can see right here is r times cosine of alpha, r times sine of alpha. And if you repair right here, what is passed to us is a matrix, and it asks to us to find the matrix which represents the original position and rotation of the robot before it got restored. So what is this? What is elements on this matrix are representing. This first column is one of the columns which represent the orientation obtained the factor. So right here is r times cosine of alpha. Right here is r times sine of alpha, and right here is L. Okay, so now let's take the calculate alpha. Right here we get rid of L. So is 6.578 divided by minus okay, and let me copy this. And this is equal minus 2.748. And this example from the second edition is not using the notation A10. It don't even calculating using the notation arctangent. Okay, so is arctangent of minus 2.748, and that is equal, oops, alpha is equal arctangent. Let's use the octave to calculate this. So is alpha dag equal A10 2D, and we don't even calculate this relation. Right here again is y and x. So let's see, y and x. So is 6.578 and right here is minus 2 octave is doing something which is calculate already on the correct quadrant, is doing because actually right here we got minus 17, and let me draw this. That is the first, the second, the third, and the fourth quadrant. And is on the second quadrant, is on this quadrant. And using the appendix A, now we have to analyze this. We have to here sine of alpha and cosine of alpha being positive and negative respectively. So we will find on the appendix A this information. If sine is positive and cosine negative, the angle is on the second quadrant. Then is 180 minus arctangent of alpha. The same as we got on the octave. And now calculating R. So R times sine of alpha is equal. We can use both relations, sine of alpha, or sine of alpha, or cosine of alpha. 6.578. So R is equal divided by sine of 110, and R is equal 7. And this way we calculate the matrix before the position and the rotation of the robot got restored. And now I'm seeing that is a good opportunity to finally define what is the fourth column is representing and is essential. As I said, throughout the video, as we approach the content, we will find what this is representing. Now remember the technique that we use it to solve the example in which we wanted to restore the position and the rotation after a series of transformations. So actually we already have saw this, and we will apply again. So right here, restoring the origin of the frame in OA. Remember this technique that we apply in order to restore the original orientation of the reference frame. I said that position is orientation. So the technique is do a rotation around the A-axis. And I also do this analysis with you. The A-axis, it corresponds to the same transformation, the same characteristic matrix of rotation as we do above the Z-axis. So let's find the characteristic rotation matrix that we do above the z-axis, this one. And right here is not theta, is alpha. And I will write this applying the technique. Actually, I will copy what I have right here. Okay, right here. Okay. Okay. And now if we substitute alpha right here, cosine of alpha, sine of alpha, and minus sine of alpha. But if I'm not wrong, is minus sine of alpha. Okay. So that is the matrix which represents the position in the original position and orientation of the robot before it got restored. So we are still referring to the example before the example 2.17 of the second edition. So again, we have done, as we are referring to transformations on the cylindrical coordinate, we are doing two transformations of translation, two linear motions, and one transformation of rotation. And given this series of transformations, if you wanted to know what is the original matrix before it got restored, so that is kind of counterintuitive. Okay, so I will just substitute the elements with values. And that's it. On the next video, we will solve more examples. And now, from the third edition, before we got spherical coordinates. And for now, it's all. Thank you.